Okay, let's try to wrap up with this problem, trying to show that the expected return time to x is finite. What we've shown is that it is finite when the expectation of both of these random variables, y and m, are finite. And so let's think about what y was. Y was the very first attempt on which we've succeeded in exceeding or equaling state x. So qx, the capital Qx, is the probability with which we reach state x or beyond. Right? It's a sum over all qy greater than or equals to x. And therefore y is just a geometric random variable with success probability qx. Right? In particular, you see that y is equal to k, meaning that we succeed in exceeding or equaling state x on the kth try by failing to do so, k minus 1 times, and then here's our probability of success. So these are our k minus 1 failed attempts at reaching state x multiplied by the probability of our first success. So this is just a definition of the geometric random variable, and if you look up any basic textbook on probability, you've probably seen this in 120A or 120B, that the expected value of y is just 1 over qx. Notice that this being finite gives us our condition for irreducibility and also recurrence. When qx is when qx is greater than 0, this expectation here is finite. When qx is 0, it is actually infinite. And so you see the relationship popping up again here. Now, what of m? So m was assigned to be the state on which we landed on. Right? We didn't have to necessarily land on x to return to it. We landed on some state that's greater than x. But then once we do so, we clearly come back to it in m minus x steps. And so now we're looking for the definition of this random variable m. Well, take a random variable n first with that has probability qx. So what's n? N is the state that I move to from 0, regardless of what's been happening. Right? It has distribution q. But I'm looking for m, which is not quite n. And the reason is that m was defined as the state on which we land on, given that we've exceeded the state x. And so by definition, then the distribution of m, right, m equals y, and y has to be greater than or equal to x because we must exceed x. M is equal to y with a conditional probability. It's the probability that we've landed on y given that we've exceeded state x. And now how do you compute a conditional probability? Well, you take the and of these and divide by the probability of the set that we're conditioning on. The probability of this and this event is equal to just n equals y because y is greater than or equal to x. And we know how to evaluate this exceedance probability. The probability that n is greater than or equal to x is simply qx, our success probability. So that gives us the distribution for m, and then you can easily compute this. And it's equal to this sum right here. And here's something interesting that you notice. So first of all, this is just the value of m times its probability. I left the qx out here, the big qx, and multiplied right through by the qy. That's the part that stays in the sum. And notice that what's interesting is that this is finite if and only if m naught is finite. So this comes back to recurrence of the recurrence condition for state 0, and this had to be the case, right? I mean, we've seen that that to conclude positive recurrence for every single state, you just had to exhibit recurrence for state 0, and so no wonder we're getting a very similar condition here. Not exact, but the idea is that this sum will be finite if and only if the same sum from 0 to infinity is finite. Nothing can diverge in the first x terms of the sum. And so the condition that this sum is less than infinity is the same as requiring the state 0 to be positive recurrent, which again is not a surprise. So hopefully that example worked out fully, helps with the homework and other problems.